Hello, welcome back to Avocet Math. In this video we're going to go over a recent AMC problem involving factorable integer equations. This problem actually appeared on the 2015 AMC 10A, and it's a good example of how an integer factorable equation can be disguised. And let's see what we have here. Consider the set of all fractions x over y where x and y are relatively prime positive integers. So relatively prime is just a fancy word for x and y do not share a common factor. How many of these fractions have the property that if both the numerator and denominator are increased by 1, the value of the fraction is increased by 10%? So let's translate that into math terms. We have a fraction x over y such that when we increase the numerator by 1 and the denominator by 1, we're left with a number that is 10% larger. I translate that into a factor of 1.1 times the original fraction x over y. Since we're dealing with an integer equation in x and y, the first step is to try to eliminate any decimal forms that I may have introduced, in this case 1.1. So let's translate 1.1 into an integer fraction, 11 over 10 times x over y. And again, we're trying to solve for xy in the set of positive integers z. So we have fractions on both sides of this equation. Let's cross multiply in the usual manner. We have 10y times x plus 1 is equal to 11x times y plus 1. Now at this stage in the problem we have integer factors on both sides of the equation, and we could actually solve this problem by comparing the integer factors, but it's a little bit complicated since we actually have three types of factors on both sides, and that gets a bit complicated. We like to reduce this to a point where we just have two factors on either the left or the right side. So let's continue to do that. Let's expand the left side to 10xy plus 10y is equal to 11xy plus 11x. And at this point I'll bring everything to the left side since that's the form I'm most familiar with, and we'll just bring everything to the left and multiply everything by minus 1 to leave us with xy plus 11x minus 10y is equal to 0. Now at this stage in the problem, our method calls for us to take the coefficients and multiply them together. 11 times minus 10 is minus 110, and add that to both sides of the equation. And this is looking pretty good. We can take the left side now and factor it to x minus 10 times y plus 11. Now at this stage we could apply the methods that we've talked about, but whenever I encounter an unnecessary minus sign in an equation, I like to try to eliminate it if at all possible. So let's go ahead and multiply both sides of the equation by minus 1. And that flips the x and the minus 10 to 10 minus x times y plus 11. Okay, I like that a little better. That's a little easier on the brain. We have a positive integer on the right. We seem to have what looks like two positive integers on the left, because y has to be greater than or equal to 1, and that basically forces x, 10 minus x, to also be positive as well. So this is looking very encouraging. So now we have to consider all possible factor pairs in 110. So we can write 110 as 1 times 110, 2 times 55, 5 times 22, and 10 times 11. Now we also have to consider the reverse of these factor pairs, so 55 times 2 or 22 times 5, and see if those can match up to the left side as well. And also, since we have a negative sign on the left side of the equation, we also have to consider the possibility that we have to represent 110 in terms of negative numbers. So, for instance, minus 1 times minus 110, minus 2 times minus 55, and so on. But what we notice from the left side of the equation is that one of these factors is certainly positive, y plus 11. And that means that since these factors come as either plus plus or minus minus, we know that the minus minus are not available. They're not valid solutions, and we only need to consider the positive forms of these factors. And so we can do that now, and Making one further observation, we notice that since x and y are both positive, that the left factor will always be less than the right factor. And so, in fact, we have the order of the factors correct here. The smaller number to the left, the larger number to the right. We don't really need to consider the reverse order of these factors, and we may need to do in other types of problems. So at this point, we've reduced this as best we can, and now we just have to basically calculate what values of x and y can we match up with these factor pairs. So for the factor pair of 1 and 110, we have 10 minus x equal 1, 11 plus y equals 110, so that reduces to x, y equal to 99 and 99. For 2 and 55, that's x is equal to 8. 55 into this equation gives y equal to 44. And for 5 and 22, we have 5 and 11 for the values of x and y. And for this last one, I see that, oh, okay, so we can't really make 10 and 11 because x would have to be 0, and that's not allowed. So we can eliminate this from consideration. So now we have these three possibilities, and we have to see which of these comply with the original statement of the problem. Again, we're looking for x and y that are relatively prime, so they share no common factor. So we see that the first one, 9 and 99, do share a common factor, so we can eliminate that. 8 and 44 share a common factor, so we can eliminate that. And we're just left with the 5 and 11, which do not share a common factor, so that's our only one valid solution to this equation set. And looking at our choices, we have 0, 1, 2, 3, and infinity. So this is obviously one solution. We have B1 as our answer.